Some things to remember about second order RLC circuits. Here are the key aspects of second order circuits. One, there needs to be two energy storage elements that cannot be combined into an L equivalent or a C equivalent. Second order systems have to have a characteristic equation that is better to analyze intuitively. And to help with that, you need to be able to determine the capacitor voltage and inductor currents at the initial point at DC and at the long term at DC. And there are three types of second order system responses: overdamped, critically damped, and underdamped. So let's go into all of these three aspects. So there needs to be two energy storage elements that cannot be combined into an L equivalent or a C equivalent. And so in this case, yes, there's two energy storage elements in series and two energy storage elements of the same type in parallel. Well, you can find an equivalency of them in parallel, and you're going to find an equivalency of them in series. And so these are only first order circuits. But when we come down here, we have two energy storage elements, L1 and C1. They're in series, they're different elements, and so they can't really be combined. So that's a second order. Here it's made up of capacitors separated by a resistor, so there is no equivalent resistance here as well. So that's a second order system. Here's another second order system called the parallel RLC, and I have two energy storage elements that can't be combined. So we have second order, second order, second order. And sometimes, yes, the second order can have more than one of the same type element, but you just can't combine them. Otherwise it reverts back to a first order circuit. Second order systems have a characteristic equation that is better to analyze intuitively. If we set up this series RL circuit and we come up with a differential equation and we assume a solution of A e to the st, well, we can draw out of that s squared r1 over l1 s plus 1 over l1 and c1. Remembering that this s is the second derivative of st and this is the first derivative. Once we pull out the exponential, you're just left with that. So where does this equal 0? Well, here are the two roots. All right. Still might be a little bit hard to see what's going on, so we put it in a more compact form with the roots of S1 minus alpha plus the square root alpha squared minus omega squared, and the roots are just different by this change of sign here. And alpha is R1 over L1, and omega is 1 over L1 divided by C1. Now we can analyze these three cases. So in the first case, if alpha is greater than omega naught, and in this example R is